I'm very happy to give our recent work on a generalization of the Nambu-Goldstone theorem. Here is my collaborator. Okay, let me start with the gapless mode in nature. So actually, the Nambu-Goldstone theorem is developed in the high energy physics. So here is the nuclei, and this here is a pion. So actually, pion is a Nambu-Goldstone boson, which is causes the nuclear force, in particular the long range region. So if you go see the other system, so there are many gapless excitations, like here is the superfluid photon, and here is the magnet. Inside the magnet, there is the so-called spin wave. And the photon is also the gapless. And if you see the surface of water, you can see some surface waves. So all these are a kind of the gapless excitation. So behind this, so there is some symmetry. So in case of the pions, there is some chiral symmetry. And in the case of the superfluids, such as the U1 symmetry, that is a particle number conservation. And if you see the magnet, so there is a spin symmetry. And if you see the photon, so there is some U1, so-called the one-form symmetry that I will explain later. And in the case of surface wave, that is the translational symmetry. So these are all symmetries are broken. And as a result, the gapless excitation, so-called the Nambu-Goldstone boson or Nambu-Goldstone mode appears. So, but the Nambu-Goldstone theorem is developed in the high energy physics, in particular the Lorentz invariant system. So the conventional Nambu-Goldstone theorem works for only this particle. So if you see the other system, so you need to some generalization of the Nambu-Goldstone theorem. So what is the Nambu-Goldstone theorem? So suppose the system has a Lorentz invariant, and in the ground state has a ground state is a Lorentz invariant, Lorentz symmetry. Yeah. So when the spontaneous symmetry breaking occurs, so in particular for the continuum symmetry, so there appears gapless excitation. That is called the Nambu-Goldstone boson. So here is a schematic picture. So the Nambu-Goldstone theorem, spontaneous symmetry breaking is defined as Q is a conserved quantity charge, like a U1 charge or energy, momentum, and so on. So here I want to focus on the internal symmetry. So if phi is some field, local field, so the expectation value of the commutation relation between the charge and the local field, if this is non-zero, that is a spontaneous symmetry breaking. So symmetry breaking is characterized by this parameter. So this is called the order parameter. So in the Lorentz invariant system, the number of broken symmetry that corresponds to the number of this operator, so is equal to the number of Goldstone bosons. So in particular, dispersion relation is linear. So energy or frequency is proportional to the momentum. This is because the relativistic system. So this relation holds. So roughly speaking, the Nambu-Goldstone theorem claims that when symmetry is spontaneously broken, that there appears some flat direction of the potential. This is a figure of the potential. So both potential are symmetric under rotation along this axis, but the minimum point is different. So if you see this potential, so minimum point is not unique. So there is some degeneracy. So this direction corresponds to this order parameter. So existence of order parameter, there is a one-to-one correspondence between the flat direction and this order parameter. That is a Nambu-Goldstone theorem claim. So why symmetry breaking is so important? So because the system is really complete, even the system is really complicated, but if you know the symmetry breaking data, then we can predict many things, like a dispersion relation and also the low energy behavior governed by the only the symmetry. So here is some example. This axis corresponds to the magnetization, and this axis corresponds to temperature. So actually, this axis is T to the 3/2. So this behavior called the Bloch law. So the all different situations satisfy this relation. And also this is so-called the Debye T cubic law. So this axis corresponds to the heat capacity, and this is a T cubic. So this behavior is actually coming from the dispersion relation of the magnon. So the dispersion relation of the magnon is actually the k square. And in this case, the energy mode, the Nambu-Goldstone boson is called the photon, so who has a linear dispersion. So as a result, this is this behavior appears. So in this talk, I'd like to generalize the theory of the spontaneous symmetry breaking to the barrier systems. So there are many possibilities of existence of a long-range force and non-relativistic system and space-time symmetry breaking, and some symmetry for the extended object, or more exotic case, that is a open system or active matter system. So here, so I don't have enough time, so I cannot cover all of them. So in this talk, I want to focus on just 3 systems. So non-relativistic system and system with extended object and open systems. Okay. So let me start with the non-relativistic system. So it is known that there exists some exception of the Nambu-Goldstone theorem. So which means Nambu-Goldstone mode with the number is different. Number of the energy mode is different from the number of broken generator. And the dispersion is not linear. So one of the examples appear even in the relativistic theory at high density. So in QCD, that is quantum chromodynamics, but at high density, it is expected that there exists a color superconducting phase. And at some phase, so this is just a technical thing, but at some phase, the so-called kaon is condensed. So the symmetry breaking pattern is simple. So SU2 times U1 symmetry is broken down to the U1. So since generator of this symmetry, the number of generators is 4, and U1 is just 1 generator. So the number of broken generator is equal to 3. So this is similar to the Higgs sector, this symmetry, electroweak symmetry breaking. But there is no gauge field here. So anyway, there are 3 broken generators. So in the relativistic system, correspondingly, there are 3 Nambu-Goldstone boson appear. But in this system, the only 2 Nambu-Goldstone boson appear, whose dispersion is linear and quadratic. So this is the exception. So if you see the more condensed matter system, as I already explained, the magnon, that is a Nambu-Goldstone mode in the magnet. So in the magnet, so there is spin, and this is aligned. So the system has a spin rotation. So if you see that this is SO3, then it's the spin is aligned, that's break down to the SO2. So in this case, SO3 has 3 generators, and SO2 has only 1 generator. So the number of broken symmetry is 2. But in Magnon, it is known that there is only one energy mode appears. The whose dispersion is quadratic. So we want to understand this situation. So we want to construct the Nambu-Goldstone theorem cover these situations. But the situation of the potential is actually similar. So when the global symmetry G is broken down to the symmetry H, then the number of flux direction is actually the same. But the flux direction does not mean the independent gapless excitation. That is the point in the non-relativistic system. So let me explain some history of the generalization. So Nambu-Goldstone theorem is developed in the 1960s. So there is some generalization in the high energy physicist by the high energy physicist. So Nielsen and Chala actually classify the Nambu-Goldstone mode by using the dispersion relation. So we already saw that there are 2 types of the dispersion relation, which is a linear and quadratic. So they classify the Nambu-Goldstone boson by using the linear dispersion, more generally the k to the odd power, and they call that is a type 1, and the other is a even power, that is called the type 2. So they showed that type 1 plus twice of the type 2 is larger than broken symmetries. So this is an inequality. But basically, this inequality holds in any systems. But after several years, so these people found some theorem. So if QA and QB is some symmetry generators, so if commutation relation, expectation value of the commutator of these charge is equal to 0, then this equality holds. So that is the number of energy mode is equal to the number of broken symmetry. So the key point is this operator, this order parameter. So in 2004, so Nambu discussed some argument. So this non-vanishing commutator is somewhat looks like these 2 degrees of freedom are canonically conjugate. So which means the canonical conjugate means that these degrees of freedom are not independent, but it's related. So that degree is the number of energy mode. So after that, so Watanabe and Browner showed some inequality by using this order parameter. So they found this inequality. So number of broken symmetry minus number of Goldstone boson is smaller than this value. So this rank means that this has indices. So this is a kind of matrix. So they found this inequality. So after 1 year, so Watanabe and Murayama and by myself show that actually that this inequality is saturated. So this equality is satisfied. So in general, so we can classify the Nambu-Goldstone boson type A mode and type B mode. So roughly that type A is a kind of harmonic oscillation and type B some at the precession motion. The number of type B is characterized by these values. That is a Q different charge is the canonically conjugate. And the left of these degrees of freedom is called the type A. Since this is an anti-symmetric matrix, so the rank is always even. So this half means that this is a pair, the number of pair causes some single energy mode. So by using these relations, the sum of these gives the number of energy mode. So you can find this relation. So let me explain this picture. So as a simple example, so this is a classical example. So this is not a field theory, but this gives you some intuition. So let's focus on this pendulum with spinning top. So rotational symmetry is explicitly broken by the gravity. So there is some gravity in this direction. So this is a classical system. So originally this has some rotational symmetry. So but this symmetry is explicitly broken by the gravity. So this pendulum is aligned to this axis. But there is still rotational symmetry along with the z-axis is unbroken. But the x direction and y direction is broken. So since this is a weak field, so there is some oscillating mode. Because the symmetry, the number of broken symmetry is 2, that corresponds to the x-axis and y-axis rotation. So there are 2 gapless modes. So you can see that this mode, oscillation of the x-axis, and also that we have the oscillation of the y-axis. So this gives you 2 exciting modes that correspond to the Nambu-Goldstone mode. But if this spinning top is spinning, so you can see some single precession mode like this. So what is behind is in this case, so this is classical system. So commutator corresponds to the Photon bracket. So then this is a rotational symmetry case. So we have the angular momentum is a symmetry generator. So Lx and Ly, the Photon bracket of the Lx, Ly gives you the Lz. That is angular momentum of the d-axis. So if this spin is spinning, so Lz is non-zero. So if this value is non-zero, then the mode x and y mode coupled each other, then that gives you some single mode. That is behind the mechanism of the type B energy mode. Okay. So now we have the 2 types of mode. So the type B mode is classified as this guy, and type A is classified as other mode. The example is a superfluid phonon, and this example of type B is a magnon. So the dispersion relation is also understood as follows. So in the classical case, so because of gravity, so this is acceleration. So that in the case of the harmonic oscillator, the frequency proportional to the square root of g. On the other hand, precession mode, the frequency proportional to just g. So there is some difference. If this difference explains so if you replace this g by k square in the field theory, so this gives you the linear dispersion. On the other hand, if you g replaced by the k square, So this replacement is a bit non-trivial, but if you admit this replacement, the type B is has a square quadratic dispersion. Okay. So these are examples of the type B mode. So this is a ferromagnet system, and this is a color superconducting system, and also this is the example of Spinner-Beck BC. And this is also the non-relativistic massive CPM model, show the some of these symmetry breaking. All these examples, of course, satisfy this relation. So actually, the number of the broken symmetry is type A plus twice of type B. So this yellow point is all the same. Well, this is the story of the non-relativistic system. So now I want to generalize this theorem to the more exotic systems. So, symmetry for the extended object. So in nature, there are several types of the extended object, like a string object, like a vortex, and also the domain wall. So you can assign the quantum number to these kind of objects. That is a generalized global symmetry. So let me explain the global symmetry in the quantum field theory. So let's consider the D plus one dimension quantum field theory. The ordinary symmetry is some existence of the unitary operator labeled by the group element. So since this is the integral of the charge is the integral of current, so you can identify that this is a D-dimensional object. So this can be understood as some extended object in the codimension 1 in the space-time. So D is the space dimension and 1 is the time. So if you have the two unitary operator, so multiplication rule satisfies the group law. That is the symmetry generator. So time independence implies that this operator is topological. So you can move this operator as you like. So, and also the transformation rule of the charged object is given by like this. So if U phi U inverse gives you some transformation. So in the case of the U1 symmetry, so this is just a U1 phase. But this is the relation. But as I said, this operator is topological. Then you can deform this operator to the something like this. So in general, the symmetry transformation rule is charged object phi. So this is the charged object is surrounded by the symmetry generator, gives you the transformation. So that is a rule in the global symmetry, the ordinary global symmetry. So now we want to generalize this notion to the extended object. Here is the summary of the ordinary symmetry. So in the ordinary symmetry, this is some pair of the codimension 1 object, that is a D-dimensional object, and charged object is just a point-like object, that is a zero-dimensional object. So which is labeled by the group element, and on the other hand, charged object is labeled by the representation that corresponds to just a charge. So in the case of the U1, that is just an integer. So now we want to generalize this notion to the p-dimensional object. So now p-dimensional symmetry is some kind of the topological d minus p-dimensional object. That corresponds to the unitary operator in the ordinary symmetry. So if you have the difference to object, that gives you the sum, that satisfies the multiplication law. And charge object is a p-dimensional, something like this. Then the transformation rule is if charge object and the symmetry generator are linked, that gives you the some transformation. That is some kind of generalization. So now charge object is somewhat extended. But here is a summary. So symmetry generator is some kind of the d minus p-dimensional object that is a topological, and which is labeled by the group element, and charged object is a p-dimensional object, which is labeled by the representation of the group. Okay. So actually, if you use this notion, so the photon actually they can be identified as a Nambu-Goldstone boson associated with so-called one-form symmetry. So that is the P is equal to 1 case. So charged object is a one-dimensional. The symmetry generator corresponds to the two-dimensional in 3+1 dimension in our world. So this object is nothing but the world line of the charged particle. On the other hand, this operator corresponds to the electric flux and the magnetic flux. So actually, in the U1 gauge theory, so electric flux. So if there is no matter field, so there is no electrons. So electric flux and magnetic flux is conserved. So that conservation law related to this kind of higher form symmetry. And the charge object is this one. So in this system, actually the expectation value of Wilson loop that corresponds to the order parameter. So if this is the area law, that is the unblock, that corresponds to the unblock phase. And this operator behaves like the perimeter law or Coulomb law that corresponds to the broken phase. So this is a kind of generalization of the symmetry breaking. So actually, in U1 gauge theory, that in 3+1 dimensions, the expectation value of the Wilson loop behave like the Coulomb law. So that corresponds to the broken U1 symmetries. So nowadays, photon is understood as a Nambu-Goldstone mode. But counting rule is more complicated. So if you see, so we already see the electric flux conservation and magnetic flux conservation. So in this case, there are 6 broken generators. So, but we know the independent gapless mode is just 2 photons. So which means that these operators are not independent. So actually, the commutation relation between electric field and magnetic field gives you some non-vanishing component. So that gives you some constraint. And in addition, there is another constraint. So as a result, that gives you the 2 photons. So this situation is a little bit complicated, but we can generalize the Nambu-Goldstone theorem to this kind of situation. So there are several interesting phenomena occur in several systems. But here is some example that's related to the generalized global symmetry. So here is so-called type B Kelvin. So in this system, so existence of the vortex related to the existence of vortex breaks the translational symmetry. So in this case, x-axis and y-axis is broken. So in particular system, the commutation relation of translation is non-zero. That's proportional to the quantum number of this vortex. So that is one form symmetry. So since existence of the vortex, this right-hand side is non-vanishing, so this is a signal of the type B. So because commutation expectation value of the commutator is non-vanishing. And this is here is another example. So this is the existence of domain wall. Gives you some non-trivial gapless excitation. So in this system, U1 symmetry and translation is broken, but this commutator proportional to the domain wall number. So existence domain wall gives you the non-vanishing commutator. That is a signal of the type B. So this energy mode has a quadratic dispersion in this case. So another interesting system is U1 gauge theory coupled to some topological operator and coupled to the domain wall. So here is some example of the action. So the pi corresponds to this domain wall. So suppose this is an external field, and that's the configuration of this guy somewhat domain wall structure. So this is a simple system, but if you calculate the dispersion relation of this system, so you will find some quadratic dispersion of the photon. So if there is no this term, so there are two photons, that is right-handed with the right-handed helicity and left-handed helicity. But if this term exists, so the only one gapless photon exists. So this actually can be understood as the commutator. So in this case, this is a net charge of this system. So this corresponds to the electric flux conservation. But in this case, commutation relation actually proportional to the domain wall number. So again, this is a commutator expectation value of the commutator is non-vanishing. That is a type B photon. So the type B mechanism explains this behavior. But this is related to the high generalized global symmetry. This is a symmetry for the extended object. So actually we generalize this relation, including this kind of higher form symmetry. Then we found this kind of relation. So this is a straightforward generalization, but this part is a bit complicated. But we can do the generalization. That we found. Okay. So this is the second part. So lastly, I would like to show another example, another generalization, so-called the open system. So here is some example of the open system. This is the open quantum system. The quantum system coupled to the environment. So another exotic system is a so-called active matter system. So this is these are birds. So this is a active particle. They move by using their internal energy. So the important point is in this system, the energy or momentum are not conserved because the interaction between the system and the environment. So this is quite different from the previous cases. That is an isolated system. So now the question is, can we discuss the spontaneous symmetry breaking phenomena in this system? So actually the symmetry breaking occurs. So for example, this is some simple model, so-called the Bichek model. So here is the equation for this model. So here is the update of the time, the position is given by this. So this is just an ordinary relation. So the position plus momentum times small t gives you the next position. And the point is that this model, the point of this model is that this interaction, the velocity is the absolute value of the velocity is constant, but the direction can change by interacting with different particles. So this arrow corresponds to the different particle, but the direction corresponds to the direction of the velocity. The angle can change by the interaction and noise that corresponds to the interaction between the system and the environment. So here is the interaction. So this is the R is some radius. So if you focus on this particle, so some given radius. So if you see another particle, and the next angle is given by some average of all other angles. So which means some interaction. So if you have some particle, then this particle tend to align the same direction. So here is some simulation example. So this is the ordered phase. So some parameter is different. The noise parameter is different. If there is a noise is strong, then this is this ordered phase. And if noise is small, then you can see some ordered phase. So this is some classical system. So if you consider some hydrodynamic model describing by the previous example, so you will find some hydrodynamic equations. The first equation corresponds, rho is the density of the particle, the v is the velocity. Well, this is a number conservation. The number of particles does not change. But on the other hand, this is the equation for the velocity. But the existence of the interaction between the system and the environment, so there is no momentum conservation. But this part corresponds to the non-conserved term, and here there is also the noise term. So if you analyze this system, so and let's consider a steady state. Steady state is given by some stationary point of this part. So there are two types of stationary points. So V equal to 0 is a solution, obvious solution. But V can be non-trivial. So you can find V, the ratio of the alpha over, if you choose the V square is equal to the alpha over beta, this term vanishes. And if you choose that this is constant, then other term also vanish. So this is a solution of this equation. So this gives you some symmetry breaking pattern. It's O3 broken down into the O2. then if you evaluate this fluctuation, that you can find some gapless excitation. So that is nothing. In particular, this mode is nothing but the Nambu-Goldstone mode. But the dispersion is a little bit different. So there is one propagating mode. The other mode is actually the not propagating mode. It's still gapless, but it is not the propagating, but the diffusion mode. So this diffusion mode is some property in the open system. But there is some question. So can we discuss the symmetry breaking without ordinary conservation law? So as I said, this is an open system, so there is no global symmetry. So there is no ordinary global symmetry. So to think about the symmetry in this kind of system, so let's consider the Brownian motion. So here is the equation for this Brownian motion called the Langevin equation. X dot gives you the momentum. The momentum dot gives you the some friction term and random noise. So we choose this random noise satisfy this relation. So ordinary angular momentum is x cross p. So this is the ordinary angular momentum. But because of the existence of the friction term, so angular momentum is not conserved. So this is the property of the open system. But if you see this equation, so this x is vector and u is vector. So this equation is written in the all written in the vector. So you can define the rotational. You can find a rotation symmetry in this system. So to see the global symmetry, so you can rewrite this equation to the Fokker-Planck type equation. Because there is some equivalence. Because this looks like the Schrödinger equation. The time derivative is equal to some differential operator times the probability. So you can see that this form looks like the Schrödinger equation. So that means that you can rewrite this system to some path integral form. That is called the Martin-Sear-Rose formalism. So you can express this system by using the path integral. So if you have the path integral form, so you have this action. And if you have the action, then you can define the global symmetry by using this action. So degrees of freedom is actually so this u, and this chi corresponds to the conjugate momentum that corresponds to the derivative of u. So this is somewhat similar to the ordinary quantum theory. So this corresponds to x, and this operator corresponds to the p, momentum p. So path integral written in the x and the p. So this is a similar form. So now we have the action. So we can define the this action is invariant under the term rotational symmetry. So if you transform chi to the r chi, and you transform to the r times u, and under this transformation, the action is invariant. Then you can define some net charge is given by the chi cross u. So actually this operator is conserved, but this operator is different from the ordinary angular momentum. So in the open system, so we have the two types of, so in the path integral form, so we have two types of angular momentum. And the open system have some this kind of net charge. Since we have the net charge, so we can discuss the spontaneous symmetry breaking by using this symmetry. So
sorry,
yes.
I'm typing. There's a question from Matteo. What is BT in the previous slide? I think temperature, but I'm not sure.
Okay, in chat, yeah. What is a big T? Big T. This parameter. Here is this is the temperature. So this is big. That comes from the originally comes from the Landau equation. So this is called the fluctuation dispersion relation. The fluctuation two-point function noise is equal to the friction times temperature. This relation is called the fluctuation dispersion relation. So yeah, this is the temperature. So this system is actually the classical system. So you can generalize this system to the open quantum system. So in the open quantum systems, so we have the path integral formalism. That is called the Schwinger-Keldysh path integral. So in this case, we have the the path integral is something like the from t equals 0 to t go to the infinity and come back to the original point. So this kind of path integral. So in this case, we have the forward path and the backward path. And each path has an action. And in the open system, so there is some interaction between the forward path and the backward path. So if there is no this term, that corresponds to the isolated system. So this term represents the interaction with the environment. So this is a model of the open quantum system. So in this system, so since we have the two actions, so actually these are some total actions. So by using this action, so you can discuss the global symmetry by using this action. So if there is no this term, so we have the original, this is just the original action. So suppose this is invariant under some symmetry, but the existence of this term might break the this original symmetry. But some of them are unbroken, but some of them are broken. That is the situation in the symmetry in the open system. So actually, some linear combination. So for example, the difference still invariant, but the sum is not. That is the situation in the previous classical case. So you can generalize the symmetry of the classical system to the quantum system. So here is the quantum open system. So now what we found is when the spontaneous symmetry breaking occurs, so here is the inverse of propagator. So this 0 point of this operator gives you the dispersion relation. Can be expanded by using the momentum. So actually the isolated system, so these coefficients can be calculated. And in the isolated system, so we have, this corresponds to the commutation relation. So if the expectation, non-vanishing expectation value of this commutator gives you the this term, single momentum term. So that explains the type B energy mode. And if there is no this term, that corresponds to the type A mode. So this is the isolated system. So now we extended this notion to the open system. So now we have J is a conserved current, and here is the explicit breaking. By the interaction with environment. So environment play a role of the explicit breaking term that modify these coefficients that give, so since there is some single momentum part, and here is some I here, so that gives you some imaginary part. So interaction with the environment causes some diffusion mode. So that is a mechanism that is a mechanism of this mode. So we found some more general relation by using the matching formula like this. So its time is running out. So let me summarize my talk. So in this talk, we discussed the generalization of the Nambu-Goldstone theorem. So in general, so there are two types of energy mode exist. So that is the type A mode, and the other is the type B mode. So in the isolated system, here is some relation. The expectation value of the commutator gives you the type B mode, and the others gives you the type M mode. So here is the non-relativistic system, and also that we discussed the symmetry for the extended object. And even for the extended object, this relation works. So of course we need some generalization, but this mechanism works. And further, we discussed further generalization to the open system. In the open system case, there is some unconventional mode, that is a diffusion mode. So this relation is no longer hold, but still we can analyze the such a system. Okay, thank you very much for your listening.
Thank you so much for your nice talk. Is there any question? Okay. I have one actually. Maybe I missed, but when you were talking about in hydrodynamic systems, in the system there is no conservation law, but there is some non-conserved terms.
Yes.
And normally you calculate the expectation value of some symmetry generators, and this gives us the NG modes. But in the system, where is the expectation value?
Okay. So in this system, the velocity, the expectation value of the velocity corresponds to the classical solution. So if beta is negative, So if beta is negative, then the V equals 0 is a solution, stable solution. So if V is a positive, so beta is positive, and the V equal, velocity is equal to 0 is unstable, then the stationary point gives you the some non-vanishing velocity. So that corresponds to the, so this is a classical case, so there is no ordinary expectation value, but yeah. This classical solution corresponds to the non-vanishing velocity. So since this is a vector, so actually this is the order parameter. So if you transform the this vector by the O3 transformation, the direction has changed. So yeah, this can be understood as order parameter.
Thank you.
So which means if the bird flies the same direction, so that breaks the rotational symmetry. The fluctuation of the this direction gives you the some diffusion mode. That can be understood as the Nambu-Goldstone boson mode.
Okay, there's no anomaly, conservation law, but there's a fluctuation. And
Fluctuation.
okay. And in this condition, you can understand there should be a NG modes. I mean, because of fluctuations.
Yeah.
Okay. Thank you. And is there any other questions or comments?
Maybe I have some question. So I hesitate to ask because I come from I know very little about physics, so please indulge me. So I have the impression that in first is there. I don't remember if you have used type 1 and type 2, then type A. So the energy systems that refers to similar things.
Type 1 and type B is classified by the dispersion relation, and on the other hand, type A and type B is classified by the expectation value of the commutator. But ordinary case, the type 1 corresponds to the type A,
okay,
and type 2 corresponds to the type B.
Okay.
But
so we know that.
Yeah.
Sorry.
Yeah.
Go ahead.
You can construct some exception, but type 1, you can construct some artificial system, type 1, but the dispersion relation is type A energy mode, but the type B, type 2 dispersion. You can construct some artificial system, then you can construct some exception. So in general, these are different, but the ordinary system in nature, type A energy mode corresponds to type 1, and type B energy mode corresponds to type 2.
Okay. And eventually, there is no other atypical type. So there is these two categorizations are the only one. We cannot go further. So because
we cannot go, if you focus on the dispersion ratio, I mean the number of degrees freedom, these two, type A and type B is the all possibilities.
So this has a relation with later on you have talked about the like a decomposition. What I have understood is it's like we are decomposing some the operators on symmetry generator and charged object. So I just want to know if there is some mathematical background of this, if we can see it as some decomposition of operators, or mathematically how we could.
This second part.
Next. Yes. Yeah, like in this, yes, this kind of.
Okay. The difference between the symmetry generator and charged object is actually in this case, this operator is topological. So which means you can you can change you can deform this operator as you like. But so that does not change any physics. But on the other hand, if you change this operator to something, this operator to something like this, the physical value does change. That is the difference. So this is this is non-topological and this is topological. That is the difference. The symmetry generator is topological, meaning that the physical quantity does not change by the deformation of this operator.
I mean, for example, when we have a real situation and we want to see them in this kind of vision, so the decomposing in the topological component and and the physical component. I mean, mathematically, is this some interesting question mathematically to be able to have this decomposition, or is it trivial to have this? Because I mean, in real life, I would expect that these two components are intertwined in some sense. So seeing them in a decomposed way, is this? My question is a bit general, so maybe it's just if this kind of decomposition.
This decomposition can be done by in the simple case. So there exists some so the correspondingly there is some D minus P form. So actually that so in this there is some correspondence. There is some these element is D minus P form. So let's say J. So that is a closed object. So and these objects they exist some P form. So if you say this guy, so this is not closed. The topological, what I mean is these objects correspond, the differential form is a closed object. And in this case, this is not closed. This is a difference. So in the case of the electric U1 gauge theory, so the equation motion something like this. So this is this corresponds to electric field, and also that we have this guy. So this is also closed.
Okay. I think I captured that. It's it's something related of seeing different forms. in closed and non-closed. Okay. One other remark is about I think just a remark about the when you have written the group law, and I think in the slide before this one, I mean, can you go back one step? I think. Yeah, the after, yes, the one after, I think. Just a remark about the operation, the group operation here. So here we have phi. So my vision is I see this like phi is like some test function and Vg as the operator. So the right hand side we have. If I understand right, Vg is like a neutral element of the group here, because in the right hand side we have an operator applied to a function, and in the left hand side we have like some conjugation.
Right. Yeah.
Yeah.
And the Vg is actually the representation.
Representation. Okay.
Yeah.
And so for the equation of the transformation, it is correct to write. I mean, Usually is like an operator applied to a test function. Let me see it this way, and you have we have the inverse of UG. So so it's just the how it is mathematically written seems to me a bit strange, but yeah.
So you mean this guy?
The equation transformation, and we have an equation.
This one?
Yes. Could you explain just what does this equation mean?
So this means.
Yeah, I mean, maybe the question is a bit strange, but the right hand side we have an operator applied to a test function. So is this the case?
So this is actually the so mathematically. So I don't know what should I say. So this is
okay. Sorry
if
the question is yeah, if the question is strange. So yeah, it's not. So my only like what seems a bit strange is just in the right hand side, it's like we have an operator applied to a test function. So the result is a function or an element of the group, and the left hand side we have it's like we have applied the operator on the left. So it's like we have an operator applied to the test function, which is an element. Then it's like the operator is applied on the left, not on the right. So it's like it's just something related to how it is written. So this is the only.
Okay. Yeah, in quantum theory, so the example is UG is something like UQ and phi and.
Okay, sorry. So it's like a notation convention. Okay, sorry.
Yeah. And this can be written, and also the Q phi. So let's say this is commutator is equal to -5. Then you can calculate this guy by expanding the theta, and this gives you the phi minus I theta phi plus Phi, blah, blah, blah. Then this gives you the phi. So this is a yeah.
Okay.
Algebra. So that is yeah, this corresponds to the BG. So that corresponds to this is the U1 generator. Theta is so this is the element of U1, and this is representation, one-dimensional representation of the U1. So yeah.
Okay, I see. Thank you very much, and sorry for.
Yeah. So, thank you. Yeah, thank you for your question.
There is a question in chat, I think we are okay.
Yeah. Yeah, okay.
Hidaka, could you check the chat part? There's a question in there.
Okay. I think we are working on algebra. The UG phi and the UG inverse are in the same algebra, which is not commutative. So we are working on the algebra.
I think it's just a comment about the question I have raised right now about the notation of the equation.
Okay.
It's related to that. Yes.
I see.
Okay, if there is no any comments or question, we would like to thank you again for giving this nice talk. And see you.
Okay, thank you very much. Yeah.
Thank you very much.
Thank you. Thank you very much.
And see you the other presentations.
Yeah. Thank you very much. Yeah.
It was a nice talk. Thank you.
Thank you.
Thank you also to the organizers.